Don't have much left. Okay. The first one is find the 3 cubed roots of -1 minus square root 3i, and write the answer in trig form.
Okay. The 3 cube roots of that. This is a difficult subject to understand. What they're basically looking for is some complex number that when you multiply it by itself 3 times equals this number. Okay? So, this is where we want to use de Moivre's theorem.
Okay.
Hold on. Roots of complex numbers. All right, if the polar or trig representation of a complex number is this. We went through this yesterday. That is the polar or trig, either term is the same, representation of a complex number. Then the nth root of r times cosine of theta plus 2 pi k all over n plus I sine of theta plus 2 pi k all over n, where k is 0, 1, 2, up to n, minus 1. And those are the nth roots of the complex number z. All right, let's see. Hold on, I'm looking for an example of one that is very similar to this. They want the fourth roots of I do these about once every 2 years, if that. So I'm not used to doing them. However, I think I can figure this out. Let's see. Well, I can figure this out. The example they have in the book are the fourth roots of z equals 5 times cosine of pi over 3 plus I sine pi over 3. So if we can get this complex number written in polar form, then I know how to do it. So what is the polar form of the complex number that you've given me?
So would that be, so we would take the
What's R? We need R, we need theta. Those are the two things we need.
So is R the, what's it called, the absolute value?
Well, it's the square root. Think of R as being, if it was x and y, it'd be the square root of x squared plus y squared. But when we have A and B, think of those as being x and y. So R is the square root of this squared plus this squared, which is 4. So the square root of that is 2. So R is 2. What's theta?
Wait, how would that be 2?
Let's see, the square root of -1 squared plus negative square root of 3 squared. Well, -1 squared is 1. This is 3. 1 plus 3 is 4. Square root of 4 is 2. Am I making a mistake? What are you saying?
Well, I'm just, like, it seems like it should end up being, oh, it's the square root of 4. Okay,
It's
sorry.
R squared that's equal to A squared plus B squared. So R is the square root of both of those.
Okay.
Okay. So we got R. The next thing we need is theta. And then we'll have the polar form of the equation, and then we can go into the nth roots of it. So theta, this is the same as vectors. So
Okay.
think of -1 as being the x-coordinate of the vector and -3 as being the y-coordinate of the vector. So what would theta be?
So that'd be the inverse tangent of root 3 over, or negative root 3 over -1.
Plus pi.
Oh, right.
Because the x is negative. So what is the inverse tangent of root 3?
Is that gonna be 30 degrees?
In other words, if I draw my 30, 60, 90 triangle, that's root, no, hold on. No, we got it backwards. It's going to be 60. Opposite, when I draw these two special triangles, I call them my unit triangles because the side opposite the smallest angle is always 1. And that side is root 3, and that side is 2. So the tangent of 60 degrees would be root 3 over 1.
Oh, okay.
So theta, being the inverse tangent of root 3, is going to be pi over 3 plus pi. That's 4 pi over 3. That's how we get theta. And now we have the polar form. All right, so now we need to put it in this form down here. So we want the 3 cube roots. So n is 3. So first of all, we want the third root of 2 times the cosine of 4 pi over 3 plus 2 pi k over 3. Plus I sine of 4 pi over 3 plus 2 pi k all over n, which is also 3. So these are going to be our 3 cube roots. Let's let that equal to z for the moment.
Okay.
What's the deal with k? K goes 0, 1, 2, 3, 4, and so forth, up to n minus 1. So in this case, we're going to let k equal 0 for one of the roots, 1 for another root, and n minus 1 being 2, that's the third root. With me?
Yeah.
All right. So our 3 roots are going to be the cube root of 2 times the cosine of, well, let's do the 0 case first. When k is 0, we just have 4 pi over 3 divided by 3, so that's 4 pi over 9. Plus I sine of 4 pi over 9. So that should be one root. We'll put a little 1 there. The first root. Second root. Now, in this case, k is going to be equal to 1. So we're going to have 4 pi over 3 plus 2 pi. Well, 2 pi is 6 pi over 3. So that's 10 pi over 9. Plus I sine of 10 pi over 9. That's the second solution. Boy. This case, k is 2. So we're going to add 4 pi to this number. Well, 4 pi is 12 pi over 3. So that would be 16 pi over 3, 16 pi over 9. Cosine of 16 pi over 9 plus I sine of 16 pi over 9. Now, all 3 of these end up with a complex number in standard format, a plus bi, because after all, that's just a number and that's just a number. Well, that is just a number.
Okay.
So when we plug this into our calculator and distribute this, we'll have an a and an I, a bi. Now, the hardest part about these problems is understanding the answer. Interesting. The book I have does not come up with an answer. It leaves this as the answer. In other words, these are the 3 answers. Now, they're not the same. And that always gave me a little bit of trouble. How can they not be the same? In other words, if I say, what are the square roots of 1? You say 1 and 1. Or -1 and -1. Notice that when I ask for the square roots of 1, I don't get two answers that are the same. In one case, 1 is one of the square roots of 1, but in another case, -1 is one of the square roots of 1. So if I want the 3 cube roots of 1, I'm going to get 3 different numbers. Just like I got 2 different numbers when I wanted the square root of 1. Now, on your test, was this multiple choice?
No, this was free response.
Okay. Well, I don't know if it's worth our spending time coming up with what these 3 numbers are. In other words, this is clearly just a calculator problem. And we're probably better served by going forth. Do you kind of get the concept of how K works here?
Yeah.
And K always is 0, 1, 2, up to n minus 1. So if I was looking for the 8 roots of that complex number, K would count up to 7. And 0 through 7 would give me 8 roots.
Okay.
Okay. In fact, one of the problems in my book under this subsection is find the 8th roots of 1. Who knew that there were 8 roots of 1, right? I mean, we always thought that it was 1 and -1. But once you bring in complex numbers into the picture, you can have 8th roots of 1. Again, that is a hard, and now in this problem, they actually came up and told you what they were. Let's talk about that for a moment.
Okay.
The 8 roots of unity. Well, one of them ended up being 1 plus 0i. That's 1. The second one ended up being root 2 over 2 plus root 2 over 2i. And you will discover that if you multiply that by itself, you have to do it 8 times? I don't think so. Let's see. If we square that, what do we get? We get this squared is 2 over 4 plus 2 of these, so 2 times root 2 over 2 times root 2 over 2i plus 2/4 I squared. Well, what does that give us? That cancels. That times that is 2, so those cancel. And I squared is -1, so that becomes -1/2. So I end up with 1/2 plus I minus 1/2. So I end up with just I. I think the problem I'm doing is just multiplying it together. I think you got to multiply it together 8 times. In other words, that to the 8th power should equal 1. If that is one of the 8 roots, yeah, it's not that squared that should equal 1. It's that to the 8th power. Is that something you can do easily on your calculator? I can probably do it relatively easily on Wolfram Alpha.
I think I have I on my calculator. I'll look real quick.
I could try doing it on my calculator, although I can't remember ever doing a complex number to the 8th power.
Yeah, I see the I button. I could probably do
Go
it.
ahead. Do it and see what you get. Let's make sure that that's 1, so that we're understanding this correctly.
Is there a certain mode that I need to be in, or should it just...
As long as you can write a complex number, square root of 2 over 2 plus square root of 2 over 2i,
Okay.
and then take that whole thing to the 8th power. I mean, one way we could do this is to use de Moivre's theorem. That's what it was designed to do, was take complex numbers to some power. But we can check our answer here and gain understanding if you can do it quickly. I can do it on Wolfram Alpha, I'm quite sure. Just make sure that that's 1. Yeah, it's going to be.
Yeah, it's 1.
Okay. And the third root is 0 plus I. And we know that I to the 8th power is 1. I to any power that's a multiple of 4 is 1. In other words, I to the 4th is 1, I to the 12th is 1, so forth and so on. So, yeah, that's exactly what we're doing here. All right, this is informative for me also. Yeah, negative 1 is another 8th root of 1. In other words, you multiply that, take that to the 8th power, you get 1. Negative I is one of the roots. That to the 8th power becomes obviously I to the 8th, which is 1. And then, of course, the negative this, negative that, I is one of them. All right. I'm starting to see how this works, and I've always had trouble understanding this. How you can have 8 roots of the number 1, but clearly you can. Now, the question I've always asked myself is, can you have 10 roots of the number 1? I think you can. In other words, there's nothing magical about the number 8. You can have as many roots of any complex number as you want. Just like the question you just had was, what are the 3 roots of that complex number? Well, the question could just as easily been, what are the 5 fifth roots of that number? And everything works the same. In other words, we change n to 5, r stays the same, k would count up from 0 to 4, giving you 5 roots, and so forth and so on. So I believe that any complex number actually has an infinite number of roots. You can actually say, what are the 100 roots of 1? Come up with 100 different answers, because you just count k going from 0 to 99, and that n would be 100. All right. Hopefully that clears it up. I mean, you don't need to memorize these formulas, do you?
I get a note card on the final,
Right.
so
Okay, good. Because these are hard to memorize.
yeah.
Yeah, no. As long as you have a note card, then is all it is just plugging in. Okay? So the key thing with vectors, parameters, and polar equations seems to me recognizing that theta is the inverse tangent of y over x and all that other stuff that goes with it. That's if x is positive, it's y over x plus the inverse tangent of y over x plus pi if x is negative. And that same logic applies to complex numbers where you're trying to figure out what theta is. When you take a complex number and you put it into polar or trig form, like this, you need to figure out what theta is. And it's the same thing. It's the inverse tangent of this number over this number plus pi if this number is negative. What else? Do you have anything more?
No, that was the last one on my
That was it.
quiz there.
That was a doozy for sure. That
Yeah.
might be one of the tougher problems in the book, actually. Oh, and not really. I mean, when you think about it, it's not that hard to do. As long as you have a note card that has the formula, it's just plugging into the formula. So actually, it becomes rather easy. The hard part is conceptually thinking about it. How do you have 3 roots of this number? Or how do you have 8 roots of the number 1? That's the hard part, always has been for me. But I'm beginning to understand that more now. When does this stuff due?
Monday.
Do you have it all done?
Yeah.
Okay. You good to go?
Yeah, that was the last one. Thanks.
Yeah, if you have any that you're not sure of or you still have to do, call me and we can do another small session, a half-hour session, whatever you need. I would do one thing before turning this in as your answer. Come up with what the real answer is and multiply it, cube it, to make sure you get that complex number that you started with. You know what I'm saying?
Okay. Yeah.
Okay, now this is going to convert to a number, but you're going to have to multiply it by the cube root of 2. So that's going to be your A. Your B is going to be the sine of 4 pi over 9 times cube root of 2. So that's going to be your B times I. In other words, when you convert everything to numbers here, you're going to have an A plus BI. Make sure that Z1, the A plus BI cubed, equals this, what you started with.
Okay.
And in fact, yeah, once you do that, that'll prove to you that you did it correctly. And you may not have to do this, but this should also be the same thing. In other words, this is going to convert to a complex number, and that complex number, when cubed, should equal your starting complex number. Same thing with the third one. And since I haven't done it, I'm not 100% sure on my definition of theta, but I'm 99% sure. And I will bet you that if you convert this to that complex number and cube it, you'll get what you started with. And that'll prove it to you. And then you can turn it in with total confidence.
Okay.
Okay? And besides that, he may want it. If the question said give your answers in A plus BI format, then you don't want your answers as Z1, Z2, and Z3 functions of cosine and sine. I'm not sure which one. Just because the book gave these kind of answers doesn't mean that's what your teacher's looking for.
Alright, thanks.
Daniel, good luck. Are you done with tests, or do you still have a final to take?
Yeah, my final is either Thursday or Wednesday next week.
Wow. Okay. So I guess we're going to have a Tuesday night session.
Yeah.
And like I said, if you need more, let me know. I got
Okay.
all day off tomorrow, and I got a lot of times on Sunday.
Okay.
Next week's going to get crowded, even though it's not yet. All right. Daniel, I'll talk to you Tuesday.
Alright.